steam is not something new to human society. Almost 2,100 years ago, was already the potential of steam was already discovered by Greeks. And then humans kept on improving the steam, let's say, generation and utilization with the steam engines, several steam engines. You could see 500, 600 years ago, such steam systems were used, and then 100 years ago, I don't know if you, most of you can see running these steam engines on the trains operating on trains. And today we have, so in the starting it was only the atmospheric pressure, very small amount of steam was used. Basically you fire wood, generate steam, connected in pipe, and then steam is coming out from these nozzles, and these things starts moving, and you make use of this rotational power, right? 1 bar 50, very small amount. Now we are talking about almost 300 bar of steam generation, 1500 tons per hour, gigawatt of power plants. So we have come a long way. So as I said, we will go back to the basics. That's a typical temperature pressure curve. As we said in the morning also, higher the temperature, higher is the pressure, or the other way around, higher is the steam generation pressure, higher will be the saturation temperature. Right? That's the liquid side, that's the steam side. The temperature enthalpy curve for water looks like this. Somebody mentioned something like a supercritical state. So you kept increasing pressure. At certain point, the property of water and vapor are more or less similar. So that's this point, supercriticality. That's the superheated, saturated vapor line, superheated, saturated liquid line. And on the left side is the subcooled region. On the right side is the superheated. So if you have conditions in this area, we are in superheated state. Actually not so visible, but I'll guide you through. So that's how a steam table looks like. And what steam table provides you is all the properties of steam. Sorry, this is not readable, but 2 or 3 things we will talk about. So there are 3 for energy balance or heat balance. There are 2 or 3 main things. What's the enthalpy of liquid state? What's the enthalpy of vaporization? And what's the enthalpy of superheating? So you could see here, I read it for you, it's not readable, but here you could see that's the enthalpy of liquid state. It's around 420 at 100 degrees centigrade. This you can calculate back from your formula, MCPDT. If you remember, CP of water 4.187, go from 100 to 0, 0 is your reference state, it's 490, which you can see here. Similarly, you have enthalpy of vaporization also, which is somewhere around 2243 at this temperature. And you could see enthalpy of liquid plus this will give you enthalpy of vapor. Right? Now, this steam table is currently only for saturated condition. So, enthalpy of vapor, what is mentioned here, is for the saturated vapor, saturated state. But if you increase the temperature of steam, heat the steam further, it becomes superheated. And you apply on the liquid side this formula, you will apply similar formula on the steam side or the vapor side. The only difference would be Cp would be for the steam. So like Cp for water is around 4.2, it's somewhere around 1.92 for steam. So similar way, if you have superheated steam, enthalpy of your saturated steam plus MCPDT, whatever temperature you are superheating above saturation temperature, that will give you enthalpy of superheated steam, right? Do you remember what's the name of this diagram? Anybody remember? remember boiler diagram? So that's the, once again, pressure enthalpy. We saw earlier temperature enthalpy. This is pressure enthalpy boiler diagram for water system. So this curve is familiar from the previous slide, right? Now we have different curves. This represents entropy, and there are other curves here. This represents your vapor fraction. So we saw in previous sessions and in earlier slides as well. So you can use thermal energy of steam by condensing it. You can subcool water. You can have superheated steam. So in coming 5-10 slides, we will see how all these processes are represented here on this slide. Right? So the first one would be, so let's say we have 10 bar steam, right? 10 bar corresponds to 180 degrees centigrade. This comes from comes from this curve. So somewhere around 10 bar, we are at 180 degrees, right? Okay, so as I was saying, if we have 10 bar steam, from the steam table we know our enthalpy is 2780 kilojoule per kg. Vapor fraction is 1. We said it's saturated steam, right? And this point A is represented somewhere here, because we said earlier that's the point, that's the curve for saturated steam, right? So if you have vapor fraction 1 is saturated, and 10 bar and 180 degree represents somewhere here. So you could see 10 bar with 2780. Yeah? So we are somewhere here, right? And if we talk about condensing the steam, condensing means we are at the same pressure, right? At the same pressure. We are just changing the vapor fraction from 1 to 0. As we said, this is the saturated liquid line. This is the saturated vapor line. We were here, we started here, and we cool it from here to here, thereby reducing the vapor fraction from 1 to 0. At this point, we can already read or calculate even based on MCP already see what's the enthalpy of our steam at point B, somewhere around 763. Means if I go from point A to B, which is saturated steam to saturated liquid, we can extract how much? Almost 2000 kilojoule per kg. Let's stay here. Yeah, this 2000 kilojoule per kg energy can be used, thermal energy. And pressure of steam depends on temperature at which heat is required. So let's say heat is required for your process heating at 150 degree, and you know heat transfer from high to low temperature, and there is a certain delta T. We will talk about this 20 degree, 30 degree for different application, and that's how you specify or decide on your temperature of steam. And temperature of steam is nothing but pressure of steam based on the curve. The temperature pressure curve what we saw, right? So normally at cooking tea or boiling milk or water at home, normally we do it at 1 bar because 100 degrees centigrade is enough, right? Then to increase efficiency, you apply pressure cooking. What exactly we do with pressure cooking? We increase the pressure, and that means the temperature of water inside the pressure cooker is increased. Yeah? So that's how you increase the efficiency, right? Process heating is somewhere around 80 to 250. We said this morning 300, somewhere around this range, 250, 300 degrees centigrade. You need process heating. Right? We also talked about the steam flow from one point to another point. It creates a lot of pressure drop. So this also we need to keep in mind. going from A to here, but B is still here. That's my mistake. So once again, we start with the same 10 bar, 180 degree saturated steam, and instead of condensing it, now we are going to expand it. So earlier we saw extracting heat from steam at same pressure. Now we are expanding it from 10 bar to 1 bar. Right? So on the logarithmic log scale. Right? So another small mistake here, it should be 1 actually. So we go from 10 bar to 1 bar. You could see enthalpy at the starting point was similar, 2780. Go from here to here. Enthalpy is somewhere 2250. Means with this state change, how much energy we are extracting? Only 524 right, per kg of steam. And you could see that going from reducing the pressure, you can only extract very small amount of energy, right? While going on this line parallel to the x-axis, you can extract a lot of energy. Right? So to extract similar amount of energy, you really have to go. If you want to extract this minus this, you really have to go very high pressure to very low pressure, which is practically not possible. Right? So if you want to extract kinetic energy from steam, what would you prefer? What would you prefer? You move a little bit up it on this curve. That means generate steam at higher pressure. Thereby you increase the enthalpy of 0.8. There you could see 2803. So earlier we saw the enthalpy was 2780 at 10 bar, but now I am generating steam at 30 bar, right? So starting point enthalpy is increased, right? Point B is similar, 1 bar. Now I am extracting a little bit more energy, right? 10% more, 524 to 587. Still not comparable to what we had with the condensation, right? Because yesterday somebody said the major part of energy content of steam is in latent heat. Right? What else we can do? What else we can do? We can superheat the steam, right? So we are not at the saturation curve, but now we move from saturation curve to superheated region, thereby increasing the enthalpy of point A. Right? And with this, now you have much more energy extraction. Right? So we are already coming to this point that if we want to have kinetic energy extraction from steam, it's better to have wide difference between pressure between point A and B, right? And if you want to have process heating or thermal energy extraction from steam, higher the temperature required for process, higher will be the pressure required for your steam generation. Right? Okay, this you pretty much understood or explained. And as I was saying earlier 19th century, they were generating power using very low pressure steam. Nowadays, supercritical. Somebody has also heard about ultra supercritical power generation. It's at 300 bar. 300 bar somewhere here. So it's already here. So supercritical was 240 somewhere in this region. But now they are talking about 300 bar somewhere in this region already. So what we saw till now is the steam and conceptually basically how its properties are and how we can utilize the state change of steam for our industrial purposes. Right? So heating and electricity production, that's what we already talked about. The two major applications we found. Right? So let's take an example. We need to heat a certain process steam from 10 kg per second from 30 degree to 150 degrees centigrade. Cp is 2.5. Can you please calculate what's the duty required? What will be the duty required in kilowatt? That's my mass flow rate. I have the CP, I have temperature in, temperature out. What will be the duty? How much? 3,000? I don't know, let's check. Anyone else other than 3,000? 3,000? So I was not wrong. So this delta T we already talked about. We already know that the steam, the heat flows from high temperature to low temperature. But you cannot have heat transfer from 29.01 degree to 29 degree. You need certain temperature difference. And significance of this temperature difference is higher this delta T, because delta T is the driving force for heat transfer, like for mass transfer driving forces. Sorry? Concentration difference, right? Right. So similarly for heat transfer driving forces, temperature difference, and rate is like driving force divided by resistance, if I remember correctly. Right? So if you have lower temperature difference, your driving force is low, that means your heat transfer rate is low, you need a lot of heat transfer area. Right? So delta T we already talked about. That means, let's assume for this application we need 20 degrees centigrade delta T. So we are heating the steam from 30 degree to 150 degree, right? And we said minimum temperature difference we need is 20 degree. That means on this end we need to have steam at 170 degrees. That fix is our pressure from the same curve what we saw in the starting temperature pressure curve. Saturation curve, which is somewhere around 8 bar. So at 8 bar, we go to the steam table, what we saw earlier. That our latent heat of condensation is this much, 2032, sorry, right? Which is 5.3 tons per hour. Right? So what we have so far, we started here. We know we need 3,000 kilowatt of duty to be supplied, right? Then we already calculated that 5.3 tons per hour of steam is required. We go from point A to point B, what we saw in the first temperature enthalpy curve, right? And thereby extracting 3,000 kilowatt of energy, right? Where this steam will be generated? So already by burning fuel. So the same numbers we use, what we use so far. Let's assume that we are burning natural gas, 47 megajoule per kg, lower heating value, already gives you what's the amount of natural gas we need. Okay, this steam is generated, you need water. So this water is kind of recirculating. You take the steam, it goes back here, comes back here. It keeps circulating within the system. When you burn natural gas, you generate a lot of flue gases. So to burn this natural gas or methane, you need air. So if you do a simple psychometric calculation, that will give you amount of air based on very simple 79-21 mole composition, nitrogen and oxygen, right? That gives me already amount of flue gas, right? Let's assume if we have two such consumers, 3000 kilowatt here, 3000 kilowatt here, suddenly our natural gas consumption increased from 330 to 626, right? We are generating steam not 5.3, but now 10.6. So you have, let's say, two consumers for your thermal energy. Yeah? Now let's get this one. Yeah, let's go. So in the previous slide, we saw we have two consumers which requires heat at similar temperature. But now assume we have two different consumers. One requires heat at 150, another one requires heat at 200 degrees centigrade. Right? So based on this 150, we calculated earlier that the steam temperature required is 170, but now suddenly we need steam at 220, right? So what you will do, you will burn natural gas here, generate steam at 170 or 8 bar. For this application, you generate steam at higher pressure, probably 23 bar, right? This also is coming from this similar same TP curve for the steam what we saw in the start. Right? But actually, it's not a good idea that you have two steam generation systems separately, right? What you can do, first you generate steam at high pressure, supply steam at high temperature or high pressure to this consumer, and the remaining steam you can simply let down, right? With this, what we did, we saved all these systems here, right? So one is high pressure system, one is low pressure system. Instead of this, you will utilize only one high pressure system, generate steam at high pressure, and supply it at two different pressure levels. Right? Same thing if we see, or try to locate on the model diagram, will look like this. A to B, you go from flashing the saturated steam, right? So if we flash the steam, or let's say if we reduce the pressure of steam, what will happen? You will have some condensation. And why is that? Generally, it's not normal for other gases or other components, but for steam. Why is that? Does somebody know? So latent heat of steam it's unfortunate that we cannot read it, but latent heat of steam, how does it change with the temperature? So at high temperature, latent heat of steam is lower. That means if I need certain duty and at high temperature, the amount of steam required is more because latent heat is low. Right? Imagine we have saturated steam at higher temperature, latent heat at this temperature is low, and suddenly you reduce the pressure. So at condition B, your latent heat is more, right? And if you assume it's a adiabatic process, somewhere this energy must come from. And this energy will come from condensation. That's why whenever you reduce pressure of a saturated steam, you will always have some condensation, right? Exactly where. So as I said, as pressure increases, latent heat of evaporation of water decreases, right? And this increase or delta in latent heat must be supplied by some part of steam condensed, right? Now here you could see, based on condensation temperature or pressure, we have almost 20-25% of energy is still left in the steam. Actually, it's not steam; it's after condensation it becomes water, right? So I think we saw 2,700 to 490. So almost 25% of energy is still left, condensed water. And as I said, condensed water will be recycled back, so it's a closed system. So if we see that in the TQ diagram, so this is a typical temperature enthalpy diagram. What we see here, before that, So we did this, right? And we have a lot of, we saw in the morning also there was a lot of waste heat available in the flue gas. You want to recover it, right? So we already recovered a lot of energy here, right? But we can make use of some energy from this flue gas as well. That's what we see here. We're cooling the flue gas from T1 to T2. This is typically, we saw in the morning also 150, 160, and then gas goes out of the stack to atmosphere, right? And steam generation at 6 bar, which corresponds to, I don't know, 160, 170 degrees centigrade, right? So steam generation means you supply a lot of enthalpy at the same temperature. That's why the curve is like this, right? You cool the flue gas from certain temperature up to this temperature. That's the minimum approach temperature we talked about. In our example earlier, we saw 20 degrees. Right? We'll see in the coming slides what are the optimum temperature difference for different applications, different services. But for a typical flue gas and steam generation, it's somewhere around 14-50 degrees. So that's 40-50 degrees. So this is the recovered heat from flue gas, but this is what is kind of lost, right? Now we do steam generation. What you want to do is you want to generate steam at high pressure, right? So if I am generating steam from flue gas, what we will see here, if I, instead of 6 bar, if I generate steam only at 10 bar, right? And I know that's the temperature difference, and beyond this point on the left side will be the energy lost, right, in the flue gas. So higher the steam generation pressure, more is the energy lost to atmosphere, right? But sometimes this pressure is defined by your requirement, process requirement. Probably like we saw a process stream to be heated from 30 degree to 150 degree. This defined 170 degree, which in turn means 8 bar, the pressure of steam generation. So higher the steam generation pressure, more will be the loss. But what you can do, you can generate steam at 2 different pressure levels. We saw that in one of the example, where for one application you need 220 degree, for another one you need only 150 degree. So you generate it at 23 bar and 8 bar. Right? That's typically a plot plan how a industrial site looks like. And we're talking about here maybe 200 meter by 200 meter. That means you generate steam, but you also have to move it around. Right? Maybe your one exchanger or one consumer is here and another one is here. So you will have steam headers transferring your generated steam. What it means? It means surface heat losses. So 220 degree steam header, you will have a lot of heat losses. And we saw if these headers are saturated steam header, any heat loss will result in before temperature drop, condensation, right? Because it's at saturation temperature, so any heat coming out from this system will result into condensation. So if you have, what can happen if you have condensation in your steam pipes, you will have water droplet. And we already know the density difference between steam and water is huge. The water is somewhere around 1000 at 1 bar, and similarly steam is somewhere around 30. So if you have sudden decrease in density, this can create water hammer. So droplets can travel very fast and hit the bends of the pipe where the pipe is bending somewhere else, and they are so fast that they can break the pipe. So it's a major issue. So what normally is done, every 20-30 meter or sometimes 100 meter, you have steam traps, right? It's a kind of equipment where you trap any condensation of water. Right? Any water is condensed. The pipes are on grade, so they are slightly slow. Any water condensed goes into these steam traps, and they work in this way that only the condensed water comes out and no steam is coming out if these are operated properly, right? So if you look at the energy balance, energy in, out, what we are putting in is the LHV of fuel, right? What is coming out is steam used in heat exchanger or boiler, right? What are the energy losses we saw so far? Surface heat losses. We talked about these pipes, long pipes within your plant, and how we can reduce the surface heat losses. Insulation. And the insulation thickness, you increase in insulation thickness. Sorry?
Critical thickness of insulation.
There is a critical thickness of insulation. So it's not always increase the insulation thickness and your heat loss will go down. Sometimes it even increases because you are increasing the area. And you are hindering the heat loss, but you are increasing the area, so the heat loss is actually Q by A. And if area increases, your
Q is also increases.
Q also increases. So we have mainly the surface heat loss and the chimney losses. Chimney loss is the energy which we cannot extract from flue gas. We have to send it to atmosphere via chimney. The leakage, we talked about these steam traps. So as I said, if they are operating properly, but most of the time, unfortunately, they do not operate. They do not trap condensed water, but sometimes they also remove valuable steam. So that's also kind of loss. Water as such is not corrosive, right? But water mixed with carbon dioxide or any other dissolved gases, or not all, but some dissolved gases is highly corrosive. So in such systems, you need to put some chemicals in order to inhibit corrosion issues, right? Since you put external components, external things, if you do not take them out, they will start accumulating within the system, right? So you have to do blow down to take out, to avoid accumulation of these chemicals, right? So that's also a source of losses, energy loss. And once again, as we saw for the hydrogen plant also, at several locations we saw is always a trade-off between capex, opex. So for steam system, it's also a very delicate balance between capex, opex. So, one example we discussed in the morning, you have steam velocity 25 to 40 meter per second. That's a typical range for your header. Higher the velocity, what will happen? Higher the velocity, higher is the, higher the velocity of steam in the pipe, what will be increase? Higher is the pressure drop. I think somebody said already in another session. So higher the velocity, higher is the pressure drop. And what will happen if we have higher pressure drop in steam lines? More condensation, more losses, right? But high velocity also means you need very small pipe. So you can save on capex.
Area is small. Area is small,
but and area is nothing but money, because area times thickness is actually what you pay to your.
I think it's the satisfied equation of continuity as well.
Can you elaborate more?
No. Actually, PV, the which satisfies the equation of continuity. So if we decrease the area, so pressure will increase. When it means squeezing pipe.
Yes. So area means the flow area, the diameter. Smaller. Yes, exactly. So it's always a trade-off between capex opex. So far we had a look on how we use steam industrially for heating purposes, thermal energy extraction. And now we'll spend another 5 minutes, 10 minutes on how we use industrially for power production. And so that was the first steam engine, or let's say steam use shown or reported 2000 years ago. I said earlier, we moved from this very simple thing to supercritical, ultra supercritical, gigawatt scale power plants. Right? So basically what happens is you convert the chemical energy of your fuel to the heat capacity of flue gas. So you transfer heat chemical energy or fuel to the flue gas as thermal energy or heat capacity, and then transfer this one to steam and expand the steam and extract kinetic energy, move your generator to produce power. And we will not talk about the steam turbine generator in these slides. So earlier for thermal energy expansion, we moved from here to here. We also saw basically if you move from here to here, we can also extract energy. And it's better if you are expanding steam. It's always good to have very high pressure difference between point A and B. Or we can also increase the enthalpy by superheating it. Right? So we superheat steam, so that's the superheating. Yeah. So out of 3 different scenarios, we saw that this is the best way. The lowest the pressure here, better it is. Highest the pressure here, better it is. Higher the superheat temperature, better it is. So same example, we have natural gas, we burn it, that's the amount of flue gas. That's the amount of steam we produce at 30 bar for this example. 235 is the situation. We go and turn the turbine of the STG and generate power somewhere around 300 megawatt. But to produce this 3 megawatt, we saw earlier we need somewhere around 300 or 250 kg per hour of natural gas, but now we need much more because the efficiency here is only 28-29%. And why is that? Because enthalpy of steam coming out of the STG is much higher. It's not totally condensed. In the thermal example, we saw that the enthalpy was much lower here because we already condensed it completely. So once again on the same TQ diagram, you could see that's the steam generation pressure. We already talked about this. If you move this line up, more will be the chimney heat losses, right? So for steam generation, you need high pressure, right? So for power production, if you are burning fuel, you will have a lot of chimney losses theoretically. But in reality, you will not send flue gas at 400-500 degrees centigrade to chimney, right? Because that will be a big mistake because a lot of energy will be lost. So what do you do normally? You go to the dual steam system. We already talked about this, 30 bar, 6 bar. Another way would be there's a lot of energy left here. What we were saying earlier, it will be condensed and energy will be lost to atmosphere, recycled back. But what you can do, you can extract this energy. Right? You condense from vapor fraction 91% to 0 vapor fraction, completely condense it. So generally this will be rejected. We'll see in coming slides. Instead of rejecting it to atmosphere, you can use it for something else. Right? So once again on the same diagram, you see we start from point A, even higher pressures, 80 bar. We increase this. We increase the energy extraction further with per kg of steam because we are going even higher with the pressures here. So higher the pressure, we realize with this that amount of energy we can extract is much higher for same amount of natural gas. Similarly, for this amount of power requirement, natural gas requirement will go down. Right? So thereby our efficiency is slightly increased. Right? So we said that's actually the difference what will be translated into power production, right? So first we saw we go higher here on the temperature. Another way to increase this difference would be going lower on the pressure on this side. So instead of 1 bar, now we are coming out at 0.6 bar. That means under vacuum. So 913 or whatever was we had earlier for this point, or for this example, now it becomes 1250. So you, for the same amount of steam or same amount of fuel burned, you extract more power. Now suddenly efficiency increased to 37%. Like we applied this energy balance in our for thermal system, for the power system. Once again, energy in is whatever you burn, our fuel burn. Energy out will be the power out, the electricity you produce. And we have similar energy losses, but one new thing is the final steam condenser, because we realize we'll always have the steam condensed somewhere, right? Because as you said in the morning also, these turbines cannot accept condensing steam.
So it is a kind of energy balance across multiple units.
Yes, overall. Okay. How we can further increase the efficiency? By having two cycles. First, from the flue gas already we generate power directly. So earlier what we saw, we burn fuel, and from the hot flue gas we generate steam, and this steam we use to turn the turbines, right? But what else we can do? We can directly turn the turbine using the flue gases. If these flue gases are at high pressure. So in the earlier, let's say, power plant, you simply burn at atmospheric pressure, and then you generate steam at high pressure on the steam side. But here the combustion is at very high pressure, and you already extract a lot of energy. So we already see 2000 kilowatt we already extract. That means flue gas temperature coming out from here will be much lower, right? And then the remaining energy you extract via steam. So it's kind of combined cycle. It's not just steam, but it's the gas and steam. That's why they call it combined cycle. With this two cycles, you already increase efficiency to almost 43%. And to represent this in this TQ diagram, so that's the flame temperature typically, and you extract energy directly via gas turbine up to a certain point, right? And then you go further. So if you apply process heating, so you could see heat for process use 000, no process heating, all goes to the condenser, right? Efficiency is low. And if you can use this heat for process and no condenser, your efficiency, overall efficiency is somewhere around 90%.